Welcome to our discussion on systems of equations in two variables. If you need to do systems of equations in three variables, I have a video on that as well. And as always, feel free to fast forward to the section you want to review. Just look for this card here. Let's start off by verifying a solution to a system of equations. But first, some definitions so you understand what these terms mean. When we talk about a system of equations, it really just means a set of equations, and we're trying to solve them all simultaneously. If all of your equations are linear, then we call it a system of linear equations or a linear system of equations, duh, right? If at least one is nonlinear, then the entire system is called nonlinear. Here is an example of a simple linear, right, system of equations in two variables. You're used to seeing y equals 3x plus 2. Well, now when we deal with systems of equations, we put all the variables on one side of the equation and the constant on the other. It just makes the math easier and cleaner and kind of everything systematic that way. But it's still the same thing, still a straight line. All right, I said that we need to solve these things simultaneously, which is why sometimes these are called simultaneous equations. And the idea is that we're going to find a solution that works in all of them. And if we have two variables, x and y, then the solution is going to be an ordered pair, AB, right? Which is really just x and y, right? But you're just going to find a point that satisfies that. So you find an x and y value that satisfy the two equations. Let's look at an example of how we can verify a solution to a system of equations. So with this system here, we can verify that 3, 1, the ordered pair 3, 1, is the solution. So 3 is x, right? 1 is y. You plug those numbers into both equations and do the math and see that it works. It's a solution to both. So that means that is a consistent system, meaning it has a solution. All right, so let's see how we can solve these equations by the graphical method. Now we're only going to do this just as a conceptual thing, to kind of understand what it means to have one solution or no solutions or infinitely many solutions. The graphical method will explain that, but you would not want to try and solve systems of equations with the graphical method. That's silly. It's labor intensive and it requires, something that does graphing, and you just don't want to do it. You're better off using the substitution, or even better yet, the elimination method, which I think is the best, and that's why I'm saving that one for last. Okay, with the graphical method, you just need to graph both lines. The easiest way to graph a straight line is, right, to get 2 points, and the easiest way to get a couple points is to plug in 0. You let x equal 0, solve for y, let y equal 0, solve for x, and then plot those 2 points, and then connect the dots. Now, however, here's a note, big note in red. If you're trying to graph straight lines, whether for this purpose or for any other purpose, you need to graph a straight line, or really any function for that matter, in MyMathLab or WebAssign or a Hawks Learning System or whatever you're doing. If you're trying to graph these things with some sort of online homework tool, most of them have varying degrees of limitations as to what you can and can't graph. And normally it requires you to plot points that land perfectly on integer values. And what I mean is it is near impossible to graph the point 2.5, 3 1/3 kind of thing, or even just 2, 2.5. It has problems with that. It's much better to graph the point 2, 3 or -5, 7. You need both numbers to be whole numbers, to be integers. So plugging 0 in and solving for y is an awesome thing to do because it's the simplest thing to do. But if y ends up being a fraction, pick a different value for x until you can get a y that is a whole number. And the same thing goes when you go to the second step and let y equal 0 and you solve for x. If x ends up being a fraction, pick a different value until you can get a whole number value for x, right? You want to be able to graph points that are whole numbers when you're dealing with online homework tools. It just makes your life a lot simpler. In this case, it worked out. The zeros worked out. We were able to graph both intercepts. We did it for both lines, and then we see that the lines cross at 3, 2. And so therefore, 3, 2 should be a solution to both both equations. You can plug them both in to check, and yes, you verify that 3, 2 is a solution to that system. Now, we got a solution because the lines intersected at a point, and that makes sense, right? Two non-parallel lines will always intersect at one and only one point, and that's how we get one solution. So we say a system is consistent if we get a solution or infinitely many solutions, either way, right? And we'll see the second example in a little bit. But if we get one solution, that's because the two lines intersect at one place. If the two lines are parallel, there is no solution, and we say the system is inconsistent. All right, so you have consistent when there's solution or solutions, and inconsistent when there's no solution. So the other half of a consistent system is when there are infinitely many solutions, and that's because the two lines coincide, which is a fancy word for saying the two lines are really the same thing. So you'll see this every now and then. You'll get one equation of a straight line, and then you'll get another equation of a straight line that's been manipulated enough that you can't recognize that it's really the same equation. And once you start doing the math, all of a sudden you go, oh, these are the same thing. It's the same line. We have infinitely many solutions because a straight line has infinitely many points on it. So there are going to be infinitely many little ordered pairs of x's and y's that satisfy both of your equations because those two equations are really the same thing in disguise, okay? So consistent just means you have one or more solutions, and really you're either going to have one solution or infinitely many. You're not going to have two or three, at least not with straight lines, right? Once we get into nonlinear stuff, you could have two solutions. Think about a parabola and then a straight line. A straight line could cross a parabola at 2 points, but it could also cross it at 1 point if it, just kind of hit it tangentially at a point. And then it could also cross, below it if it's opening up, or above it if it's opening down, and then and have no solutions, right? So you can these rules only work for linear, that you have either one solution, no solution, or infinitely many. Once you get nonlinear systems, that goes out the window, and you can have no solutions, one solution, two, three, and so on and so forth, up to infinitely many. Okay. Now let's look at how we would actually calculate these things. The first method is going to be the substitution method. It's an okay method. It's fine. It always works. So if you really like it, it's not like I'm saying you can't use it. But the elimination method is superior for two very important reasons that we'll get to in a couple minutes. Okay, in order to make the substitution method work, the objective is you want to reduce one of your equations down so that you've isolated a variable, right? So you want to have y equals some stuff, or you want to have x equals some stuff. Or if your equations are in p's and q's, right, then you have p equals some stuff, or q equals, doesn't matter, right? You're basically just isolating a variable. Once you do that, you take whatever that variable is equal to. So in this case, you take the 2x plus 9, and then you just plug it in to the other. You always have to plug it into the other one. Plug it into the other variable for that y. So you would take this 2x plus 9, plug it in up here for this y, and then you're going to get an equation all in terms of the x's. Now, if you'd done it the other way and solved for x, then you would plug it in for x and you get something all in terms of y's. Obviously, you would have chosen to solve for y here in equation 2 because it's already set up with a coefficient of 1, which makes your life easier. And that's the idea, right? You want to choose the easiest path. All right, so here's working it out, right? We substitute it in. 2x minus 5 times y becomes 2x minus 5 times this, right? Equals 3. Multiply it out, combine like terms, move stuff over, isolate your variable, simplify your variable, and bing, bing, boom, Bob's your uncle. You've got x equals negative 6. Now that you have one of the variables, you plug that back into any of the equations, right? So you could plug it back into either of the original equations, or what's going to be easiest, plug it back into the one where you had solved it, right? So you'd solved y equals some stuff. If you plug it back in there, then you just get an instant answer for y a lot quicker than if you'd plugged it into either equation 1 or 2. But it doesn't matter. You can use any of them because they're all supposedly legitimate, right? As long as you didn't make any mistakes. Now that you have y equals negative 3, you have your ordered pair, negative 6, negative 3, and you should check it by plugging it into both equations. Or at the very least, if you had gotten it by plugging it into this one, then you should check it in the other one, that kind of thing. But it's best just to plug it into both. It's quick, it's easy, it takes a couple seconds, and then it's a way to make sure you didn't make any math mistakes. You added when you should have subtracted or something like that. Okay, how about if we are trying to solve an inconsistent system with this technique? And really the same thing is going to happen if you're doing this with the elimination technique. So don't think that the elimination technique, all of a sudden, this doesn't happen. All techniques, this would happen. If you try to solve an inconsistent system of equations, you're going to get this same exact situation. Just doesn't matter on the technique. We're just going to do the substitution technique because these things are set up easy for substitution. We solve for y by moving the x over. We could have easily solved for x by moving the y over. It doesn't matter. Just people are more comfortable solving for y. Then we take that, plug it back into the other equation, right? We do our distribution. When we do our distribution, we get this. We combine like terms. The x's go away. We get 6 equals 9. At that point, we really could be done. I don't know why the book insists on always reducing it to 0 equals something. But as soon as you get two numbers equal to each other, and they're different, right? 6 equals 9, 0 equals 3, 7 equals 5, 2 equals -7. Doesn't matter what the heck it is. As long as those two numbers are different, then you know the equation is false, right? Because that's impossible. 0 can't equal 3, 6 can't equal 9. At least not in a normal system, but we'd have to be in some modular system. And I digress. That means the equation's false, right? 0 doesn't equal 3, right? So 0 equals 3 is false. And that is an inconsistent system. That means we had parallel lines. Okay, so anytime you do the work and all of a sudden you get a number equals a different number and all of the x's and y's, right, all the variables have dropped out, it's an inconsistent system. You know you have parallel lines. Move on. There's no solution. What about a dependent system? That's what we call it when the two lines are really the same, right? So it's consistent because there's a solution, but it's dependent because the two things are actually the same. And you can recognize this one very easily. You can see that if you took the equation 2, multiplied it by -2, this would become 4 plus 2 equals 12, and you'd have the same thing written twice, right? But let's say they gave you one that wasn't so easy to recognize, and so you jump in with either the substitution or the elimination method. It doesn't matter which one you choose. You do some work, blah, 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 blah. In this case, we're doing the substitution method. We put it back in, we combine like terms, da, da, da. The 4's drop away, and the 12's cancel. Even if you didn't cancel the 12's, you would have had 12 equal 12, right? Which becomes 0 equals 0. But basically, anytime you have a equals A, right? Any number, so C equals C. So I shouldn't use letters because you think it's going to be variables, but any number equals any number. So if you have 2 equals 2, 12 equals 12, et cetera, et cetera. Whenever you're in that situation, well, that's true. And that's true for all x's because there's no x's left in the equation. And if it's true for all x's, then that means you just had a solution that has infinitely many solutions, and therefore you have a straight line of solutions, and your two equations are the same line. So you have a dependent system. When you have a dependent system, as we said, it is consistent. There is a solution. In fact, there are infinitely many. So instead of saying there are no solutions, you can actually list the set of solutions by basically listing the straight line. Y equals 6 minus 2x, right? That's the equation of a straight line, and that's the equation of all of the solutions that work for this system. So you would actually list your ordered pair as x comma y, but in this case you would list y as the 6 minus 2x. And it's that simple, right? So that's an infinitely many dependent system. All right, let's look at the elimination method, the one that I think is best. And the reason why it's best, two main reasons. Number one, you will most likely have to move on to a system of 3 equations with 3 unknowns. That becomes infinitely more difficult with the substitution method. You have to do a lot more steps with the substitution method than you do with the elimination method. The elimination method is a lot quicker, cleaner, and easier when you have to start dealing with a 3 by 3 or a 4 by 4, right? 3 equations, 3 unknowns, 4 equations, 4 unknowns, and so on and so forth. And they can get big, guys, depending on the subject you're doing. So the elimination method is one that you can kind of take with you throughout your math career, whereas the substitution method tends to get bulky and complicated as soon as you graduate above a 2 by 2 system. So if you have no need for going higher than a 2 by 2, substitution is fine, but most of you probably will. The other reason why the elimination method is better is it parallels very nicely with matrices. So again, in most math sequences, you will see matrices at some point, and you will learn how to solve these systems of equations using matrices. Well, the matrix methods, the idea of swapping rows and doing row echelon form and reduced row echelon form and all those types of things that you're going to do with matrices. And if this all sounds like Greek, don't worry, you'll learn it at some point. In fact, I have a video on it. The the stuff that you do with your matrices parallels exactly to the elimination method. So if you're familiar with what you do with the elimination method, multiplying by constants and adding stuff together until you get zeros, that's exactly what you do with matrices, just without writing the x's and y's. So it's a nice kind of little dip into the pool, so to speak, for matrices, and then it helps you understand matrices. Because a lot of students struggle with matrices. They're actually very simple. All they are is systems of equations without the variables. If you just wrote these things down with just the numbers, just the coefficients, that's a matrix. And then the operations you're going to be doing directly mirror the elimination method. So my suggestion is learn the elimination method. Get comfortable with the elimination method. It's far more versatile and it parallels matrices. Sometimes the elimination method is called the addition method, and I'll show you why here in a couple seconds. All right, so here's our system. The goal, right, or the objective of the elimination method is to get one of your variables to match with opposite coefficients. So you want like 6x and negative 6x, right? Or 8y and negative 8y in your two different equations, because you're going to add, see the addition method, you're going to add them together, and then those things are going to cancel out. So what you want to do to make your life easy is look for easy opportunities to make them match. So let's say if this was 2x plus 3y, blah, 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 and then this one was 4x minus 4y, blah, 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 then it would be really easy to match these because you had a 2 and a 4, so you just have to multiply the top by a negative 2 to make it negative 4, right? But because neither of these coefficients are a multiple of the other, it means you're going to have to multiply both, right? I'm going to have to multiply the top equation by something and the second equation by something else in order to make them match. So now, because we're stuck in that situation where we have to multiply both of them, the next little trick to help, save you some time and keep you from making mistakes is to see if either of them are already set up with opposite signs. Since this is a plus and a minus, it's going to make it much easier and more efficient, and possibilities of making mistakes are going to be lower if we eliminate the y's. Because if we wanted to eliminate the x's, we would have to multiply one of these equations by a negative constant so that the two numbers, right, were opposite signs, like the top by 3 and the bottom by negative 2. But if you did the bottom by negative 2, you'd have to remember that negative 2 times this negative 4 would all of a sudden become positive, and that's a place where a lot of students make a mistake. So it's safest to just use the opposite signs that are already there, multiply the top by 4, the bottom by 3, and then you see that you get the opposite 12s, right? A 12 and a negative 12. And now if you add these two equations together as they are, the y's will cancel out, which is what we do here. Add them together, 17, the y's go away. Add these together, you get 153. Obviously divide both sides by 17 to solve for x, and you get x equals 9. Boy, wasn't that nice of them to give you a whole integer? Yeah, most of these solutions are going to be integers because it's nice that way. In the real world, of course, that's not the case, or just in more advanced questions. Okay, now that you have the 9, all you have to do is plug it back in to solve for the y. Now you can plug it back in anywhere. You can plug it back into either of the original equations. You can plug it back into either of these new augmented equations. It does not matter. So obviously, plug it back in where it's easiest, right? If I'm going to plug in x, I don't want to have to multiply it by 8 or 9. I want to multiply it by 2 or 3. And in fact, if I multiply it by 2, that's going to be even the easiest. So that's the one I would choose. Plug the 9 in here, right? Move the 18 over, divide by 3, and there's my y equals 1. So now I have my ordered pair of 9, 1. I check it by plugging it into both. It works for both. I found my solution. That's the elimination method. Nice and easy. All right. How about solving these systems of equations that are applied and not necessarily linear? So here's an example of a nonlinear system of equations that we need to solve somehow but they're no longer linear equations. And all these examples we've seen were linear equations. So a lot of textbooks and a lot of teachers are going to teach you this by showing you a substitution method. Not the substitution method of what we did for solving, but literally subbing in 1 over x for u and 1 over y for v. So you can turn this big ugly monstrosity into this, and now all of a sudden it's linear. It's a great technique. The idea of substitution is a really strong technique and something that you should learn because you'll use it a lot in calculus if you ever have to go that far. But it's not necessary here. If you've been watching my videos or learning from me, you know that I have a set of like 5 or 6 simple guidelines to help us solve any equation. And that's what I'm all about. Let's find one set of things that works for all equations. And the first step in solving any equation is to get rid of fractions, decimals, and grouping objects. And we know that we get rid of fractions by just multiplying by the bottoms of all the fractions to cancel them out. And that's the technique I would use here. Now I'm going to show you how to do it with the substitution method because that's how a lot of people do it, and I want to make sure that you see how it works. Then I'm going to show you how to do it with my method, and you're going to see how much easier and simpler it is. Okay, so we do the substitution, we get this. Now we have the linear equation, and once we have these linear equations, we can solve it by any method we want, either the substitution or the elimination method. All right, if we do the elimination method, which I think is the better, then we need to choose something to get rid of. Now, because once again, nothing is a multiple of anything else, you're going to have to multiply both by a number, right, to get rid of them. I would have chosen the 5 and the -2, but for some strange reason, this textbook decided to do the 6's, which means you had to multiply that second equation by a negative, which means you had to remember that a negative times a negative is a positive, which is a place where you're going to mess up. So I wouldn't have done that. I would have done the top times 2 and the bottom times 5, and life would have been safer. But in any case, you eliminate a variable, you get the other one, right? You plug it back in, solve for the one that was eliminated, and then here's where you got to remember that because of the substitutions that you did before, right, with the u substitution and the v substitution, you now have to take those and plug them back in to actually solve for x and y. So here was my original substitution, plug in the -5 that I got, do some math, figure out that x is -1/5. Here's my original substitution with v, plug in the v that we got of 1, do some math, get y equals 1, and so now we have our solution of -1/5 and 1, and you can verify that by plugging them into both and seeing that it works. Okay, so that's their technique. Here's mine. We don't like dealing with fractions, so we get rid of fractions. How do we get rid of fractions? We multiply by the bottoms of the fractions. We always start with the largest number first, hoping that it will also kill off some of the smaller fractions, but in this case, the bottoms are actually variables, so nothing is going to reduce other than that variable, right? So get rid of the first one by multiplying through by x. You multiply by x, you get 2 plus 5x over y, right, equals -5x. We still have a fraction, so we do it again, multiply everything through by y. 2y plus 5x equals -5xy. Okay, that one's done. No more fractions, good to go. You might be a little panicked here with this whole thing. What do I do with that? Just leave it alone, right? Just leave it there. Move on to the next one. Do the same thing. So multiply by x. 3 minus 2x equals -17x, right? Oh, sorry. This still has a y on it, duh. Now multiply through by y. 3y minus 2x equals -17xy. Okay, so now we have these two equations with no fractions left. Okay, so let's kind of reset the system. We now have 2x, sorry, one of those days, 2y plus 5x equals -5xy, and 3y minus 2x equals negative 17xy. No, it doesn't matter that the y's come before the x's. All that matters is that everything lines up, right? The y's are in the same spot, the x's are in the same spot, and these xy pieces are in the same spot. So whenever you're dealing with systems of equations, you just have to make sure everything lines up properly to do the elimination method, because you're going to add, right, or subtract, and then you need things to cancel, so they need to be in the right spot. Okay, none of our coefficients are multiples of each other, so we know we're going to have to multiply through both of them. And because this one's already a plus and minus, it's going to be easiest to get rid of the x's. So let's multiply the top by 2 and the bottom by 5 and turn it into, I'll put it over here. So the top by 2 gives me 4y plus 10x minus, multiply this by 2, remember? So equals negative 10xy. The bottom one by 5, so 15x, y minus 10x equals, when multiply 17 by 5, you get 5 times 10 is 50, 5 times 7 is 35, 50 plus 35 is negative 85xy. Okay, now we can add, and we get 19y equals negative 95xy. All right, if you were going to solve that equation, hopefully you can see what you would do next, and that is divide both sides by y to get rid of the y's. Now we have 19 equals negative 95x. Now divide both sides by negative 95, all right? And you get x equals negative 1/5, and we didn't have to do any of that silly substituting back in for u stuff. Now that we have x equals negative 1/5, we need to find y. Well, we can plug it back into here. That would be crappy, right? Here, just as bad, right? Because we're dealing with fractions. Or we could plug it in here or here, right? Meaning this equation or this equation, because we'd obviously have to plug them in over here. Well, since this is a 1/5 and this coefficient is a 5 and a 5, wouldn't this one be a lot easier to work with than this one? Heck yeah, so let's use that one and go 2y plus 5 times negative 1/5 equals negative 5 times negative 1/5 times y. Okay, 2y. So 5 times negative 1/5 is negative 1, so minus 1 equals negative 5 times negative 1/5 is now positive 1, so that just equals y. Move the y over, move the 1 over, and you get y equals 1, which was the other half that we got from the other solution. So I don't know about you guys, but I think this is a lot simpler, a lot more elegant, a lot easier, and it builds on a technique and a set of steps that we're already familiar with. We already know that when we see fractions, we should get rid of them by multiplying through, and we don't have to look at this and go, oh, that's right, I have to do this with the substitution method, right? It's one less kind of new recipe to learn. You can just use the old recipe that you already know. All right, let's look at one last example, one that's kind of an applied problem. In this case, we're looking at supply and demand functions, and we're going to try and find the equilibrium point. And for those of you that have done some basic econ work, you know the equilibrium point is when supply equals demand. So you just have to set these two equations equal to each other, or basically solve for when they're equal, which is what we do with systems of equations. Because they're already written in the term of one variable equals some stuff, it sets itself up very nicely for the for the substitution method, which is what we're going to see on the next slide. But you could also do the elimination method. You know, I've been a big advocate of it, so I don't want to show you something where you can't use it. You can always use it, right? The elimination method means you just eliminate a variable. And since these are both set up with ones, you're thinking, hey, I can just subtract one from the other. Stop right there. Don't ever subtract, right? The reason why it's called the elimination method, or sometimes the addition method, is you always want to add the two. And the reason why is if you were to subtract to get rid of these p's and subtract here, you got to remember that when you're subtracting a negative, you're actually adding, and you're going to mess that up. You're going to make a mistake. You're going to be rushed, you're going to be going fast, it's going to be on a test situation, you're panicked, whatever, you're stressed out, and you're going to forget that when you subtract a negative, you really add. So it's safer, less chance of making a mistake if you always add. And in order to add, just multiply by a -1, which means you change all the signs, and now you can add. P plus negative p goes away, right? -20. Add these two together, 0.002x, right? Move the 20 over, divide by the 0.002, and you get 10,000 equals x, and then you can plug that into either of these two equations to solve for your p. So the elimination method still works. Here's how you do it with the substitution method. Again, because it was already solved for p equals some stuff, it makes it really easy to just substitute in for that p, and you get the two equations set equal to each other. Combine like terms, right? Isolate your variable, simplify your variable, and bang, same exact thing, 10,000. Plug it back in to either of them, you get that p equals 72, and so there's your equilibrium point, 10,000 and 72. Okay, simple example from the world of econ. That's everything you need to know, guys. Remember, graphical is just so you can understand what's going on. Don't ever do it unless you're forced to. The substitution and elimination method are much better. Either of them will always work. Well, all of them will always work, except you really can't graph a 3x3 because now you're in 3 dimensions and that's really hard. So substitution and elimination method always work. Elimination method is better. Try to concentrate on that because that's the one that's going to parlay nicely into matrices, and it's also going to help you out when you have 3x3s, 4x4s, and so on and so forth.